In this final lesson of the unit, we're going to talk about the applications of exponential functions. We talked a little bit about these at the beginning of the unit, but now we're going to bring it all together now that we have the tools of logarithms and natural logarithms to help us solve different types of problems. So the first example here is about a radioactive substance that's decaying according to the following formula. So you can see here it's A times e to the power of negative 0.2x, where A is the original amount of material and y is the amount of material remaining after x number of years. So part A says if A is 80 grams, how much is left after 3 years? So there you're simply plugging in a value for A and a value for x and using your calculator to determine that after 3 years, there would be 43.9 grams remaining. In part B, it's asking you to calculate or determine the half-life of the substance. So to note, the half-life is the length of time required for the substance to decay to half of its original amount. So in this scenario, the original amount was 80 grams, and so the half-life would be 40 grams. So if you've noticed, I've plugged in y equals 40 and a equals 80. When you simplify this, remember that this exponent, this e with the exponent, I should say, sticks together. We're looking to solve for x. So we need to isolate for x. The first thing I'm going to do is divide this side by 80. And you'll notice there that I get 1/2. From there, we've got 1/2 equals e to the power of negative 0.2x. We cannot solve for this exponent just by looking at this, so we are going to take the log of both sides, and in this case, since we're working with e, we're going to take the natural log. So we have the natural log of 1/2 equals, and we bring this down in front, negative 0.2 x ln e. From there, we know that ln of e is just equal to 1, so that essentially disappears. We're left with this, and then we're just going to divide by negative 0.2, and this will go on your calculator. So it will take almost 3.5 years for this substance to decay by half. The next question is a compound interest question. The thing to note is that you will always be given the formula that you need, as well as a description of the variables. You do not need to memorize this formula, and it's not on your formula sheet either. So here we're looking to determine the value of a $5,000 investment that earns 8.4% interest compounded monthly after 10 years. So this means that you're investing $5,000 and you're earning 8.5% every month for 10 years. So here's our formula. A is the final amount, the end amount of the investment. P is the principal, that's the amount you start with. R is the interest rate, always as a decimal. So most frequently it will be given to you as a percent. You need to change it to a decimal. N is the number of compounding periods per year. That means how often the interest is being paid. In this case, it's monthly, so 12 times a year. And the number of time in years, and in this case, that's 10. So when we plug all of that into our formula, we can see that we get 5,000 times 1 plus 0.084 over 12 to the power of 12 times 10. From there, you can simplify it. You could also very carefully just input all of this into your calculator. I like to simplify it first in a couple steps, just because if you misplace a bracket somewhere or forget a bracket, the order of operations can be thrown off. So I like to simplify it a little bit first and then put it into the calculator. And you get a total amount of $11,547.99. Now, this question asks you to determine the value.
Just a quick message to all.
Sorry about that. So here, this is the final amount. This is what the investment will be worth. I've added one extra thing here because sometimes the question will ask you to determine how much interest was earned. So this $11,547 includes the $5,000 that was invested. If you want to know just the interest that was earned, you can take your final amount, subtract your investment, and you'd be left with how much interest was earned. So this investment earned $6,547.99 in interest, but the total final value of it was $11,547.99. Example 3 uses the exact same formula, but in this case, we're looking to determine the amount of money that has to be invested at 6%. So the amount that has to be invested, that's the principal. So we're looking to solve for P. If it's earning 6% interest compounded annually, and if you need to have $5,000 at the end of 7 years. So in this case, I plug all of that information in. The only difference here is that this $5,000 is A. This is the final amount of money that's required. So $5,000 goes here. That's equal to the principal times, oops, I skipped a step, 1 plus the interest rate over the compounding periods. This is compounded annually. That means 1 time per year to the power of time, which is 7 years. Again, I like to simplify that a little bit. And then here we're looking to solve for P. So we need to isolate this. So I'm just going to divide the other side by 1.06 to the power of 7. And when you do that in your calculator, you get $3,325.29. So this is how much you would have to invest at 6% interest for 7 years to have a total of $5,000 after that investment is done. On the next page, we've got the formula for natural growth or decay. So we saw this in the very first example. So here's the formula. A equals P E R T. So the original amount times e to the power of the rate of growth or decay times time. And you can plug this in and use this formula in a few different ways. So that's what both of these examples are. In example 4, it says there are 1,000 bacteria. The bacteria is increasing exponentially. The rate of increase per hour is 0.025. How many bacteria can you expect in 24 hours? So here, the final amount is what we're looking to solve for. We're starting with 1,000. The rate is 0.025, and the time is 24 hours. Just be careful with these questions that the increase here is per hour, and the time you're looking to solve for is also in hours. You want to make sure those match. So here we just simply plug this into our formula. 1,000 times e to the power of 0.025 times 24, and you would end up with 1,822.119 bacteria. And then in the final example, we're going to use the same formula. This one is telling you have a radioactive substance that's decaying at a daily rate of 0.13. How long does it take for this substance to decompose to its half-life? So here again, we have to remember half-life means when will the original amount be reduced in half. So in this case, you can think of it as we don't know what the original amount was, so we can call that x. And the final amount will be half of x. Thing about this one is you actually don't even really need those x's. We could pretend that the original amount was 1 and that the final amount is half. What you'll notice here is if you do use the x's, they just cancel each other out. So when it comes to half-life, your final amount can just be half, and your original amount can just be 1. In the very first question we did, where it was 80 grams to 40 grams, you'll notice that when we simplified, the first thing that happened was this side became half. From there, we're looking to solve for t, which is up in the exponent. So we can't solve for this just by looking at this. We don't know e to the power of what would equal 1/2. So we're going to take the natural log of both sides, bring down the exponent, Here, ln of E is just equal to 1, and then again, we're going to divide ln of a half by negative 0.13. So it takes 5.33 days in order for this substance to decay to half its size.